In this video, we're going to talk about electronic structure. We're going to talk about shells being made of subshells and being made of orbitals. And I'm going to talk about electron configurations up to Z equals 36, as in number of protons equals 36. And we're going to draw orbital box diagrams as well. First of all, you have the periodic table, and in the periodic table, hopefully you will remember from GCSE that it's ordered in terms of proton number. So we go 1, then we'll go 2, and then go across 3, 4, 5, 6, 7. Now, really important thing for later on is that as we go across the periodic table, we add a proton, but at the same time we add an electron. So every time I go past a box, I'm adding one electron, okay, and one proton. Now, if you have a periodic table, you know that there are periods on the left, and those periods are the number of shells. So we've got a picture of sodium here. Sodium has 3 shells because it's in period 3, and you can see the 3 shells, 1, 2, 3. And it's really important that they're also called energy levels, and they're called energy levels because the energy of the electrons is increasing as you go out. To get further away from the nucleus, they have to have more energy. Okay, so as you go down, the electrons have more energy. Now, there's 4, 5, 6, and 7, and of course you would expect those to have the same number of shells, but we'll explain that in a bit more detail later on. Also, we have group numbers, and groups are normally where the properties align, okay, but at the same time it's also where the number of outer electrons is stated. So 1 electron is in the outer shell for group 1, and sodium is in group 1. You see that 1 outer electron, okay, and then we've got 2 electrons in group 2, 3 electrons in the outer shell, group 3, group 4, group 5, group 6, group 7, also known as the valence electron, which is the outer shell electron. The only difference we have is group 0 at the top. There's 8 electrons in the outer shell there. You'll also see periodic tables that go 1, 2, and then 3, 4, 5, 6, 7 up here, and then start calling this 13, 14, 15, 16, 17. Do not worry, they're still the same groups, essentially. Now, the periodic table itself is ordered and structured in a slightly different way. So if we look here, it's proton number, yes, but it's also split into subshells. So each shell of electrons has a subshell within it, and that subshell is structured in the periodic table, and you can see it. So let's start with the S subshell, also known as the S block. So if I call it block or subshell, they're interchangeable. So the block is on the periodic table, but it's the subshell, that's the electrons, where the electrons are going. So if we look here, helium is brought across from here. Helium has the same properties as the noble gases, but it's electronically, the electrons go into this S subshell, so it's still part of the S subshell, which is why it's in blue. Okay, so that's the S subshell. And then we've got the big block on the right-hand side, which is the P. You notice I talked about boxes. I said if you have 2 boxes here, so we've got 2 boxes, that means we're adding 2 electrons as we go across. We've got 6 boxes here, so we're adding 6 electrons as we go across. We then go to the D subshell, which has 10 boxes, so adding 10 electrons as we go across. Okay, and then the F, which has 14 boxes, so we're adding 14 electrons as we go across. Okay, and so the periodic table is made of these different subshells, and the subshells are part of the shells. Okay, and then you can just put the periodic table back together again. I'm going to keep it in these colours to make it obvious about the S, the P, the D, and the F subshells. The next question we're going to highlight, and this is a question that happens in the exam, is how many electrons are in the first shell or energy level. We follow a rule called the 2n squared rule, and all you need to do is take the period and then you put it in where n is, and then you'll know how many electrons are added. Now, a clever thing for the top anyway as well is that the number of boxes, which is the number of electrons normally, equals the right number. So we'll prove that now. So 2n squared, so 2 times 1 squared is 2. Okay, there are 2 boxes, as in 2 electrons being added as you go across. It's a bit more complicated when you go down there, but it's quite simple in the top 3 shells. We then look in the second shell, 2n squared. Remember, it's the second shell, second period. Okay, so 2 times 2 squared is 8. And again, there are 8 boxes. The 1, 2, plus a 6, 8 boxes, so 8 electrons, so that makes sense. We then go to the third shell. Our third shell is where it's a bit more difficult. And the reason is, once you go into the third shell, okay, you're going to get 18. Well, where does the 18 come from? Because there's not 18 boxes going across here. Okay, now it comes from the fact that this is the third shell and this is the third shell. So it goes across and then goes down. And you've got to remember it goes across and then goes down and then it goes back up again. So this is where it's a bit more awkward. But if you count the number of boxes, which is the number of electrons that are added across this third shell, it does add up to 18. So there's 2 there, 10 there. That's 12 plus 6 on the end, and then that is 18. Now, how many electrons are in each shell or energy level? Now, first of all, we can just use the 2n² rule for everything, okay? But the good thing is, and I'm quickly doing this, is you do not need the 5th, 6th, and 7th, so don't worry about it, okay? These are the ones you will be asked in the exam if you're going to be asked anything in the exam. So make sure that if you're going to get asked about number of electrons in each shell energy level, that you find out about those. Now, if we look at what subshells are in each shell, which is another question that may appear. Okay, what subshells are in each shell? We can do this from the periodic table mainly. So we can look here and go, right, okay, this is the first shell. If I go across, I only see blue boxes. That's the S subshell. So therefore, in the first shell, there's only an S subshell. In the second shell, you can see there is these blue boxes for the S subshell, and then there's the red boxes for the P subshell. So we have S and P in the second shell. So S and P subshells in the second shell. Now, if we just follow that and follow that through, we have first energy level is 1s. Second energy level is 2s and 2p. Notice all we're doing is putting the shell number with the subshell. So shell with the subshell. Okay. Now, remember, in the third energy level, we had 3s, 3p, and 3d. Because remember, it went across, then it went down, and then it went across again. Okay? The fourth energy level includes 4s, 4p, 4d, and 4f. Now, the reason 4f is in orange is because you're never going to be asked to discuss anything about 4f, because we only have to do up to z equals 36. So the z equals 36 is krypton right here. So it's krypton right there, so therefore we don't need to consider 4f. Okay? But you might come across 4p, okay? More importantly. Now, if we look at the periodic table and we start looking at the order in which they fill the shells, okay? So if we look here, we know there's 1s in the top. We know there's 2s and 2p. We know there's 3s, 3p, and 3d. Remember, that's the ones that goes across, down, and then back up again. Okay, I'm going to tell you here that you have 4s, 4p, 4d, and 4f. And you have 5s, 5p, and 5d, and 5f. Now, the order of filling is determined by something called the Aufbau principle. Okay, but essentially it's this diagram here. Okay, and that's what they use for A-levels. That's all you need to worry about when it comes to A-level. If you look at it, it goes into 1s first. Okay, so 1s first, then it goes into 2s. Then it goes into 2p and 3s. Then it goes 3p and 4s. Remember, it doesn't go to the 3d first. So what we're saying is the order of filling of these subshells, you're going to do it in this order. Okay, so I'm going to go 1s. I'm going to fill 1s first, then 2s, then 2p, then 3s, then 3p, then 4s. Then I fill my 3d. So you don't do it in numerical order once you get down to here. You do it in the order that's given in this diagram. Okay, and you have 4d, 5p, and such and so forth. You're only ever going to have to asked up to 4p, so you don't need to worry about the bottom half of the diagram. So essentially, let's start doing this using this ordering of subshells. Remember, we're putting electrons into subshells. Those subshells are part of shells. Okay. So if we look here, we've got hydrogen. Now, hydrogen has 1 electron. You can see it's got 1 electron. So I've only got 1 electron to place. So what I would encourage you to do is look at the periodic table and go, right, where's the element that I'm looking at? Well, the element I'm looking at is hydrogen, which is right there. Okay? It's only got 1 electron. And that electron is in the S subshell. And it's in the first shell. Okay? So that means I'm just going to go, right, first shell, 1. okay, and then it's the subshell S, okay, and it's 1 electron. Now the electron you draw there should equal the number of, the total should equal the number of electrons in the element. Now the number of electrons in the element is 1, I've drawn out 1, and I'm just following the boxes. Let's go to our next example of electron configurations. We can look at helium, and we can see that helium has 2 electrons. Okay, so we're going to go up to here, we go, right, where's helium? Well, helium's over here. Okay, it's got 2 electrons. What subshell is it? Are those electrons in? What shell are they in? They're in shell number 1, and there's one of those electrons there, and then one of those electrons there. So they're both in the 1s. So all we do is we go, right, okay, it's in 1, it's in s, there are 2 electrons added, so it's just 1s2. Okay, so my electron configuration of helium is just going to be 1s2, and that equals the number of electrons it has here. We're now going to use the example lithium to go into the second shell. Okay, so if you look at my diagram over here, you can see I've removed all the arrows, and then this order of filling again, we've got 1s and then 2s. Okay, so if we look here and we go, right, okay, let's add the electrons by the boxes. Right, there's the first electron, we've got to add 3 electrons, so the first electron's in s, second electron is in s as well, and it's in the first subshell. So that basically means it would be 1s2. So I've added 2 electrons in that first subshell. Okay, so then at that point, we're then going to go, right, okay, the third electron, well, that third electron's here. That's in the second. Remember, each box is 1 electron, so I'm just counting 1, 2, and then 3. Okay, so that's in the second shell. Okay, it's in the S subshell, so that would be 2s. It's only 1 electron I'm adding, so that would be 2s1. Okay, so if you look at those, we're filling in the order of the diagram. There's 3 electrons, we're counting the boxes, counting the number of electrons across, just going across the periodic table. 2 plus 1 is 3, and that's the electron configuration of lithium. We're now going to progress into the P subshell. So if we look at carbon, it's got 6 electrons, okay, and we need to know the order of filling, so let's have a look at the order of filling. So we go 1s, 2s, then 2p. So if we look at the actual periodic table and do it that way, we can go, right, 6 electrons, 1, 2 electrons, so we've got 2 electrons straight away, and that's in the 1 shell and the S subshell, 2 electrons, and then we go, right, 2, so we've counted out 2 electrons, let's count out 2 more, both in the second energy level, second shell, okay, and then the S subshell again. So that means we go to 2s2, okay, and then we're going to go across to the P. We'll go across to the P and we can say, right, okay, carbon is here, 2 more electrons to add. We've added 4 already, so we're going to do the last 2, and that's in the P. So if that's in the P, that'll be 2p2. Okay, so we have got 1, 2, 3, 4, 5, 6 electrons. We've followed the periodic table to our element. Okay, and so 1s2, 2s2, 2p2 is the electron configuration of carbon. We're now going to move on to the third energy level or shell with magnesium. So if it's in the third, let's do the filling, and you can see, right, okay, we're going to do the 1s first, then the 2s, then the 2p, then the 3s. Now, if we then look at this and go across again, we've got 1s2, 2 electrons, 2s2. Okay, so let's start right now. So 1s2. They all, after you've done a few of these, you will find it fairly straightforward, hopefully. 2s2. Okay, then we go all the way across. There's 6 boxes, 6 electrons, 2p6. Okay, so we've got 2p6. And then we've got 10 electrons we've done so far. We need to count out 2 electrons. We've gone all the way across to here, and then jump down to our magnesium, which is here. And hopefully while you're watching this video, you've got a periodic table, so you can look yourself. Okay, and there's 2 more electrons, and they're in the 3s2. So they're in the third energy level. Okay, they're S, and they're 2. Okay, so we have 1, 1s2, 2s2, 2p6, 3s2, 2 plus 6 plus 2 plus 2 is equal to 12. Okay, and that's the electron configuration of magnesium. The next example takes us into the fourth shell, okay, which is potassium. So if you look here, I've removed the arrows that we don't need, and you can look here, we go 2p, 3s, and then 3p, and then 4s. Really important thing, you do not go to 3d. The order of filling is 3p, then to 4s. Now we'll look at the periodic table, and we'll see how that works. So as before, we've got 1s2, okay, and then we are going for 2s2, 2p6, and that's all us counting across again, just going 1, 2, blue boxes, 2s2, and then 2p6. We filled 10 electrons. We're then going to go for our third subshell, so it's 3s2, and then 3p6. And so 3s2 and 3p6. Now at that point, remember, order of filling is 3p is full, and then go to 4s. Okay, so we go to 4s. So in 4s, our potassium is right there. So we've got to this box here. We then jump coming down here to 4s. There's only one electron left. So that means 4s1. Okay, so 4s1. So what we've got here is different subshells within each shell, and we've now started to see that our 4s fills before our 3d. Okay, that's a really important thing that you need to remember. Our final example is going to be scandium. Now, scandium has 21 electrons, so we're going to be counting 21 boxes. Okay, and let's have a look at the order of filling. So we're going to fill it as normal. Okay, and then we got the third. Then what we're going to have is 3p, 4s, and then we're going to jump up and fill the 3d. Okay, now I'm going to teach you a little bit of a cheat. You're only allowed to do this if the question says, if the question says you can do it, or your teacher allows you to do it. What we can do is we can do a shorthand, and we can say, right, okay, I don't want to write out 1s2, 2s2, 2p6, 3s2, 3p6. It's a lot of writing. So what I'll do is I'll take the electron configuration of the noble gas that is before mine. So for example, I'm doing scandium, and here's scandium. Scandium's right there. So if I just track back on the periodic table, the one previous to scandium, okay, so the one previous to scandium is going to be argon. So if you look here on argon, we can say, well, let's just say that we know the electron configuration of argon and put it in square brackets. And that's really important, you put it in square brackets. Then after you put it in square brackets, you will then say, right, okay, I can just do the electron configuration after argon. I'm just going to assume that I know that. And that's, your teacher will only let you do that if they think you know the previous ways of doing electron configuration, or the question will do it probably if it's in the second year of A-levels. They don't want to assess you writing out lots and lots and lots of stuff. So they just go straight, put argon, and then put whatever electrons come afterwards. So if we look here, we're on 4s. So remember, we go 3p, then 4s. 3p is within argon, so we're just going to start at 4s. There's 2 electrons in for us. Remember, we've got to get scandium, which is there. Okay, so that would be 4s2. Okay, and then remember, this is 3, so it's 3, and then go across. This is 3, and the order of filling is 3, so that's 3d1. Okay. What I do when I do the orders is, in the exam, you can put it in order number, as in just go 1, 2, 3, 4, and just order that. But you must know the order of filling. The order of filling is 4 before 3. So I always do it when I do my electron configurations. I have my 4 electrons, 4s electrons, written before I write my 3d electrons. It just reminds me that the order of filling is correct. Okay, and that's how you do shorthand. And remember, only if you're told to by your teacher or the question. Okay, and the electron configuration of a D block element. We're now going to go to talk about orbitals. Shells are split into subshells. Subshells are then split into orbitals. Okay, so that means the electrons are somewhere in space and they're within this orbital that was within the subshell, which is part of the shell. So the definition of an orbital is a region that can occupy up to 2 electrons which have opposite spins. You need to remember that definition. We're going to leave it on the next 2 slides to try and get it in there for you. Okay, now that means it can have 1 or it can have 2 electrons in it. Okay, and let's work out how many orbitals you would have per period. So per period, how many orbitals would you have? So if we look here at S, we can see there's per period 2 boxes. That means there's 2 electrons added per period. That means we can have 1 orbital. Okay. We then look at the P and we can see there are 6 boxes. 6 boxes going across here, which means 6 electrons added across the P subshell. 6 divided by 2 means 3 orbitals. Okay. Remember, those orbitals can occupy 2 electrons. That's why I'm dividing by 2. We then look at D. There's 10 boxes, 10 electrons, so 10 divided by 2 is 5. Okay, so we have 5 orbitals. And then there's 7 orbitals in F because there are 14 electrons added across the F subshell. Now let's look at the shape of S and P orbitals. Okay, again we've got our definition, carry up to 2 electrons, but where do they carry those 2 electrons? Now we have these things called probability diagrams. Probability diagrams show you where the electron most probably would be, and they're usually 2 different colours, so slightly darker colour, slightly lighter colour. And you look here, okay, we've got 2 slightly different colours, slightly darker around the edge, slightly lighter around the centre. The electron's most likely going to be around the centre, might be around the edge, okay, so it's that gradient showing you the probability of where the electron or electrons might be. Okay, and this is an S orbital, a 1s orbital. If we then look at the 2, which has S and P in it, okay, we've got the S first of all down here. Now this S has a S orbital from the 1 level, from the energy level 1, okay, which is smaller. The yellow one is from the 2 energy level, okay, which means it's larger, which means it has more energy, which means it's further away from the nucleus. Those electrons that are in the 2s orbital are further away, okay? If they're in the 3s orbital, they'll be further away again, 4s, further away, larger orbital. Okay, and then we look at the P. Okay, so the P looks a bit like a figure of 8 if you follow it like that. Okay, it looks like a figure of 8. All right, and so they simplify that down to a dumbbell kind of shape. And that means the couple of electrons are in there somewhere in those 2 lobes, okay, somewhere in those 2 ends. Now, if we want to do the right thing for the exam, we just need to be able to draw them and we need to be able to name them. So if you look here, that is just a sphere. So basically this is a 3D object, so a 1s orbital or a 2s orbital or any s orbitals are going to be a sphere shape that can hold up to 2 electrons each. And so you name it as a sphere when you do the exam. We then go to the p orbital. The p orbital, they make it look a bit nicer and they call it a dumbbell shape. And you can see this dumbbell shape. All you have to do is draw the dumbbell shape. In fact, just draw a figure of 8. That will be fine. Okay, and you need to call it a dumbbell if you're asked to name it. So these are exam answers, hence they're in green. Okay, so make sure that you know those for your exam. Right, drawing electrons in orbital box diagrams. Now, each orbital is shown by a box. So we're going to show how the electrons go into the orbitals and what order they go in. Now we need to do some golden rules for this and some exam tips, so let's do it. The exam tip is fill the orbitals in order. So the order you've got here, we've got carbon, we'll fill them in order. Okay? And remember we have 1 orbital for S, another orbital for the second S, and then 3 orbitals for the 2p. So we need to remember how many orbitals per subshell. Then singly occupy them before they're filled up. So you will fill, in order first of all, you'll fill the 1s fully, then fill the 2s fully, and then fill the 2p. Remember there are 3 in the 2p, so they'll be filled singly before they're filled up. Okay, remember there's 2 electrons per orbital, so that's really important. Okay, so right, let's actually draw the diagram. So the diagram consists of, okay, a box. So there's your box, okay, and we're going to call that a 1s orbital. Okay, so 1s orbital, and we label the electrons by an arrow going up and an arrow going down. That shows the opposite spin. Okay, so we've done opposite spin. Now we know there's only one orbital per 1s, only one orbital, and then we go to 2s. So we'll go 2s, and this will be 2s. We only have one orbital there again, so we only draw one box, and then we draw 2 electrons. So we've done our 1s2, 2s2. We now go for our 2p. 2p, and here's the problem. We have 2p. Remember, how many orbitals do we have? We have 3 orbitals. So what we do is we'll draw 3 boxes. There's your 3 boxes. They're all p, so I've just done them joined up. But, okay, typically we normally draw them joined up if they're in the same subshell. Okay, and then we have 2 electrons to place. So we just do 1. Remember our rule, fill it in order, which we have done, and then singly occupied first. So 1, 2. Don't put them in the same orbital. Okay, and that is how you draw an orbital diagram for carbon. Now we're going to do our second example, which is sulfur. You see with sulfur, we're going all the way from 1s all the way up to 3p4. Okay, remember we must follow our rules, fill the orbitals in order, so we'll fill 1s, then 2s, then 2p, then 3s, then 3p4, and we'll singly occupy them within these shells when we do it. So what we'll do is we will draw our first one, that's 1s, and then we'll go to 2s. One orbital in each one of the s subshells, okay? We then go to 2p. If you remember from previous, we have 3 orbitals in there, so 1. We singly occupy them first and then fill them up. We're doing that, remember, because we know there are 6 electrons because we've looked at this and we can see the 6 electrons, okay? We're then going to 3s. Okay, we know it's 1 orbital because it's s. Okay, and then we go to our 3p. So our 3p, 4 electrons, okay? So we've also got 3 orbitals. So we singly occupy first, 1, 2, 3, and then 4. Okay, it's really important to understand later chemistry that you can do orbital diagrams properly and that you can tell that there are single electrons, okay, in here. And we're going to do a question like that next. So what is the correct number of elements in period 2 with one singly occupied orbital? We've got our options here, and what we need to do is decide on what orbitals are actually in there. So if you look here, you have got P. If you go all the way across period 2, you have S and P, sorry. Okay, so you have S at the start and then P. Now, what we have to do is then draw the orbital diagrams and fill them up one at a time, because as you go across the periodic table, you will add 1 electron at a time. So if that's the case, we know we have a 2s. So we've got 2s, and then there's our box for our 2s, and then we've got our 2p. Remember, we've got 3 there for 2p. So we've got our orbitals. All we have to do is fill. So we know the first one is lithium, and then we'll move on. So 1 at a time, we'll go. Okay, so we have a singly occupied orbital. So we know that we've got 1. So let's do a tick for every time we've got 1. Okay, we then fill it in the order that we have been doing all the time. And the next one, there's no one singly occupied orbital here. And then, oh, there's 1 singly occupied orbital. So that's another one. So we've got 2. Another electron in. Okay. 2 singly occupied orbitals, not 1. So that's not right. Okay, and then 3 singly occupied orbitals, not 1, so we're not counting again. We've still got 2 singly occupied orbitals. Do the next one. Still got, well, no, we've got 1 singly occupied orbital now. Okay, and then we fill it up. So all we did there is we went through the electron configurations of each element, because as you go through the element, you add 1 electron, so it's a different element each time. Okay, and we realized that there was 3. So there was 3 with 1 singly occupied orbital. That means our answer is going to be C. Okay, and 3. Now these are common multiple choice questions, And so just get used to doing it. Just draw out the orbitals that are in that period that they name, and then put one in at a time, count them. Now sometimes they'll say name them as well, so all you have to do is, when you put one electron in, note down what element that is as you go along. We're now going to see how electron configuration change when it comes to ions, either losing or gaining electrons. So let's look at the rules to start off with. So our exam tip here is to look at gaining or losing electrons in a certain way. So when we look here, so you see an element loses electrons. The electrons are lost from the outermost shell, which is the subshell furthermost to the right. Okay, so when we draw them, I'll show you that. When the element gains electrons, it's gained by the outermost subshell. Okay, which is further to the right. Now this important thing is, as you go through your A-levels, you are going to talk about transition metals. So when you talk about transition metals, that is the D block. So these rules we're talking about don't apply necessarily to the D block in all situations. So that will come in a further video, and we'll talk about that in more detail. But for now, we're just going to be considering S and P, okay, not D. So if we look here, we've got the oxygen 2- ion, and if you look, you can see that we've already got the configuration here, 1s2, 2p2, 2p4. So we do our rules, and we look at the subshell furthest to the right, and you can see it's 2p4 here. We can see that there are 2 electrons that need to be gained. So all we do is we write 1s2, 2s2, 2p, and we have to write 2p6. So if we're going to write the configuration, we have to add those 2 electrons on the subshell furthest to the right. Now that is gaining 2 electrons, but what about losing? So we've got aluminium 3+ here, and that is 1s2, 2p2, 2p6, 3s2, 3p1. Okay, and we know it's a 3+, so we know it's lost 3 electrons. So all we do is we look furthest to the right, and we go in that direction, and we'll lose the 3 electrons as we go from the outermost to the innermost. So the subshell first we lose is 3p1, so we've lost that electron, and then we lose the 3s2. So that then just becomes 1s2, 2s2, 2p6. And so the interesting thing about both those is that they have the same configuration, okay, but they are different ions. So you would label it as aluminium 3+, then give that configuration, oxygen 2-, then give that configuration. And that is how you do ions for period 1 and period 2. Remember, later on we will talk about the D block in another video.